Okay, towards the end of the last lecture, we summarized how we are going to interpret scattering data. Suppose you use light scattering or neutron scattering or X-ray scattering. The key variable is this scattering wave vector K, which is essentially a measure of the observation length. This K is inversely proportional to observation length. If a K is small, we are looking at large length scales. If K is large, we are looking at short length scales. What is short length scale? What is a large length scale depends upon the system. For a single polymer chain, the key variable is radius of gyration. If we want to measure radius of gyration of a chain, and then we want to have the observation length to be larger than radius of gyration. That means we want K to be small. K is smaller than 1 over Rg. Okay. On the other hand, if you want to interrogate internal structure of this object, for example, a polymer coil, then I'm looking at observation length, which is shorter than the radius of gyration, then I need to go to larger values of K. So in order to design your experiment, we need to choose the right wavelengths, the right scattering angles in a way that you are able to explore what you want to observe, what you want to monitor. Okay, so this is basically the concept behind how we are going to design scattering experiments and how we are going to interpret the data. And in the case of a single polymer chain, I showed you the two limits. The scattering intensity that you measure in a laboratory is proportional to the form factor in dilute solutions. And then form factor has this limiting behavior when K times Rg is smaller than 1. That is, K is scattering wave vector, Rg is radius of gyration. For small angles relative to this 1 over Rg, and I will be able to determine molar mass and also the radius of gyration. And if I were to take this expression, take the reciprocal of that, and if I plot 1 over I of K versus K squared, and then it's a linear plot. And the intercept gives me 1 over N, therefore we can determine the molar mass. And the slope gives me Rg squared divided by 3N. And I know N, we know 3 of course, therefore we can determine Rg. So in this experiment, we determine Rg and N. On the other hand, if you go to, you work with the scattering wave vector K, for example, the incident wavelength of the beam, and then the scattering angle, and if you are in this limit, then the scattering intensity is proportional to 1 over K power 1 over nu. Therefore, if you do a double logarithmic plot of I of K versus K, the slope will give me this negative slope is 1 over K, right? Therefore, slope log plot slope will give me negative 1 over nu. So it determines the size exponent. Also, as I pointed out here, you go back to this kind of a measurement. You make several molecule weights, synthesize, say polystyrene, but different molecular weights. And then you measure Rg in molecular weight. Then from the relationship between Rg and N, you can also get nu. So that's the experimental protocol in general. Okay, so what I ended up in the last lecture was some experimental verification of this. Right, I showed some experimental verification of this. For example, in this plot, here I am plotting based upon the literature from that beautiful paper, radius gyration versus molecular weight, double logarithmic plot, and the slope is half, 1/2, as expected from a Gaussian chain. This is for polystyrene and cyclohexane at 35 degrees. In the same way, if I go and do the higher angle, right, that using X-ray scattering, instead of light scattering, I'm using X-ray scattering, where the wavelength is small. Then if I plot the I of k, I should get, for Gaussian chains, I should get 1 over k squared. So since we are using X-rays, since the lambda is small, I'm in the high k limit. But in terms of angular dependence, k is proportional to theta, because sine theta is theta for small angles, like 1 degree, 2 degree, and 3 degree. Therefore, I of k is proportional to 1 over theta squared. So if I were to plot I of k times theta squared versus the theta, I should get a flat result. There should not be any dependence of I times theta squared versus theta. That's what we see for Gaussian chains, right? And you could take this as a homework problem in your mind. Why do I get a slope of 1 here? Look at this. This is a straight line that is going through the origin. This spot, when I go to higher angle, I get I times the theta square is a linear in theta. So that means, let me write it down. That means, so I for here in this region, I theta square is proportional to theta. That means I is proportional to 1 over theta. That means I is proportional to 1 over k. That means nu is equal to 1. Remember, we had a general result. I of k should go like 1 over, right? I of k should go like 1 over, remember this? I of k goes like 1 over k to the 1 over nu. That's the general result. This means nu is equal to 1 in this limit. That's because, right, if I have a chain like this, and I go to higher k, when I go to higher theta, I'm going to higher and higher k. K is scattering wave vector, higher and higher k. That means my observation length is becoming smaller and smaller. I go in such a way that I'm looking at only in that region, right? My observation length is of that comparable to that distance. In that distance, although this is a random coil, Gaussian coil, it looks like a rod. It's a rod-like. If it's a rod-like locally, then nu should be 1. And that's what we are seeing in this region. So in this experiment, as an example, right, I get Gaussian chain statistics, right? And then I get rod-like statistics, although it's the same polymer, because my observation length scale is now much shorter. Therefore, I'm exploring only distances of that type, this type or this distance or something like that, okay? And that's what we did in the last lecture. So that's basically a summary of this. But the surprising thing is, we know that the Gaussian chain is a freely jointed chain. We looked at, when we talked about a chain like this, we talked about only the connectivity. This is connected here, this is connected here, this is connected here. We did not think about this interaction. This is the excluded volume interaction. Excluded volume interaction, right? Which we introduced already. We did not do this so far. But so it's almost like a miracle that we are able to, experimentally, we see this exponent nu is equal to half at the real system, right? The temperature is now 35 degrees, right? And the real polymer cannot be a phantom. That means they are not interpenetrate, they cannot cut across, because when the two monomers come close, there will be enormous amount of repulsion. It is unphysical to think that this monomer is going to penetrate through, that is pass through this monomer, right? It's not possible at all. So the question is, why does this happen? Why do we even observe Gaussian chain statistics for real systems, right? And then if I change a system to decalene, I do not observe this exponent. Instead of cyclohexane, I have same polystyrene, but I have decalene now instead of cyclohexane, I do not observe this. But on the other hand, if I take decalene and go to this temperature, 15.2 degrees Celsius, right, then I get this exponent half. Okay. For this solvent at this temperature, I get this result. For this solvent at this temperature, I get the same result. So this is an information that we need to appreciate and understand. Where does this come from? How do we understand this? In order to make an understanding of this, what we need to do is we need to think about the realistic system. Let's not assume that the chain is passing through each other, cutting across through each other, because that's not physical. So let's try to understand the role of extra volume interaction. And that is today's lecture. We're going to talk about extra volume interaction today. Okay, so let me go back to the slides where we left off. So this is where we left off. Let me go to today's discussion. Excluded volume interaction. So let's imagine, right? Let's imagine a coil, right? What I want to know is, let's imagine a situation where I have a polymer chain coming like this, right? This is a part of the chain. And this is in a solvent molecules, right? So when we think about this in general, there is going to be a solvent-solvent interaction. There is one solvent molecule, another solvent molecule. So solvent-solvent interaction. Right? And then there's going to be a solvent polymer interaction. There is a solvent molecule, this is a monomer, that's going to be a solvent polymer interaction. Polymer segment, if you like. And then we are going to have a polymer-polymer interaction, right? There's going to be a polymer-polymer interaction. So in general, when you throw in a polymer chain or synthesis of polymer chain in a solvent, there are going to be basically 3 interactions between polymer segments, polymer and solvent, then solvent-solvent. So how are we going to understand or compute this polymer-polymer interaction, solvent-solvent interaction? This is going to be very difficult because, remember I told you about a solvent like a decalin or cyclohexane, temperature, and lots of chemical details, right? So today, we do not know how to compute these interactions precisely. Even with all the modern computers, we are unable to precisely compute the various interactions in current phase. But on the other hand, conceptually, we know what to expect. So let's say, as a consequence of all these 3 interactions, right? As a consequence of polymer-polymer interaction, solvent-solvent interaction, polymer-solvent interaction, let's assume there's a net interaction energy. Let me write this to be U-R-I-J. There's a net interaction energy where this distance is R-I-J. So the distance between the ith segment and the jth segment is R-I-J. Let's say there is a net interaction energy coming from all of them. This U-R-I-J is a combination of all these 3. This interaction, this interaction, this interaction. So this is an effective intersegment interaction mediated by the solvent molecules. This is something we can imagine. This is not difficult to think about. Let's think about it. And I wish in a real classroom, right, when we are sitting together, we will be able to make arguments which are intuitively obvious. Let me draw a cartoon of a U-R-I-J. Okay, U-R-I-J as a function of R-I-J. As you can imagine, when this monomer is far away from this monomer, there will not be any interaction, right? So the U-R-I-J when these two monomers are far away, the interaction would be essentially zero. So it will be somewhere here, right? Interaction would be, say, it'll be something like this. Right? But on the other hand, if Rij is very small, that is coming very close here, when this jth monomer comes very close to ith monomer, right? Quantum mechanics takes over, right? You cannot have two monomers to sit at the same location. They cannot be in the same location. There will be a tremendous amount of repulsion when the two atoms come close together or two monomers come close together. Therefore, what I would expect is for short distances, this URij should be very high, somewhere here. It'll be or even higher, right? So what I would expect then is, right here, somehow when I decrease the distance from far away to short distance, it is going to transform, this function is going to transform from 0 to infinitely positive value, large positive value. But we also know from our experience that when you take molecules and lower the temperature, that is, when you lower the, like for example, you take a gas, and when you lower the temperature, it becomes a liquid. And the reason why that happens is there's a van der Waals attraction between the molecules. And then when they become, when the van der Waals attractions are promoted by lowering the temperature, for example, and there will be condensing into a liquid phase, and then further into a solid phase. Therefore, I would expect here a picture like this one. This is what I would expect for the shape of the inter-segment potential interaction. This is what I would expect. But do I know how to compute this exactly? No, the answer is no, because I told you we do not know how to compute these things very accurately. And also because it depends on all chemical details, whether I have a toluene or a decalene or a cyclohexane, whether it's a polystyrene, polybutadiene, polyethylene. So it all depends on chemical details. But nevertheless, there are two important things. One important thing is the strength of the interaction. There is one, this is a measure, the depth of this potential, that gives me strength of interaction. If it's a deeper well, it's a strong attraction, right? Strength of interaction. And then the location of this minimum, right? Attractive minimum. This one, this distance is, that gives me range of attractive interaction, range of interaction, right? And both of them depend on chemistry. Oh, sorry. Both of them, this and this and this, depend on chemistry. Namely, it depends on the particular system, particular combination of the polymer and solvent, right? So what I'm going to do is I'm going to parameterize this chemistry in terms of what is called excluded volume parameter. So I'm going to come up with, right? I'm going to capture, that is, I'm going to parameterize these details the chemical details as excluded volume parameter. Okay, I want to emphasize the word parameter. Okay, this is not a volume. This is not, you should not consider this to be an excluded volume. That is, right? This is a parameter which accounts for, which captures the strength of the interaction and range of the interaction. How much attractive, effective interaction there is going to be, that is captured by this extra volume interaction, extra volume parameter. Okay, and how do I define that? I want to define that as a representation of this potential energy, which in turn depends upon Rij, the distance between two segments, right? So let me define that in the next cartoon, right? So I already told you, oops, sorry. I already told you Rij, this is Rij, and it's going to look like this, right? This is what I wrote down, looks like that. And now I'm going to define this quantity, the extruder volume parameter, V. This is the extruder volume parameter. Again, I want to emphasize this is extruded volume parameter. Okay, it's a parameter, right? This I'm going to define to be, I'm going to define it today. We'll come back to this in a couple of lectures later. I'm going to write this to be half, sorry, maybe I write differently. 1 minus 2 chi L cubed. What is this? We will come back to this later on. Right now, I'm just going to call this for convenience. I'm going to call this to be Flory-Huggins chi parameter. I use a different color because I'm just introducing this, and we'll come back and understand this a little bit better later on. Okay, but I want to make a connection between today's concept of extruder volume parameter and what we are going to see down the road. Okay, so when I say extruder volume parameter, is related to this parameter which we shall see later on, which is chi parameter. What is this parameter representing? It represents this integral. Oh, sorry. D cubed Rij. Okay, that's the three-dimensional vector of Rij, right? Times 1 minus e to the minus this is Urij by kT. Boltzmann constant times the temperature. So for a particular system, whatever Urij is for a chemical system, that appears in here. And divided by kT, because therefore I gets the Boltzmann weight or Gibbs weight, if you like. And then this is called the radial distribution function, a pair correlation function, etc., etc. Doesn't matter. I'm just giving you a definition of the extruder volume parameter for our problem. But then, depending upon the chemical details of the polymer and solvent, we'll have a unique value of V, because this energy profile would be unique for a particular pair of solvent and polymer, and of course the temperature appears in here. Similarly, if V is unique, so is chi. Chi is also going to be unique. But I can guess how this parameter is going to look like if I change the temperature, right? Because I have Urij, which has this shape. For short distances, it's repulsive. For a very large distance away, nothing happens. But for intermediate distances, if the temperature is right enough, this becomes attractive. U is attractive because this is negative, right? So this is 0, that is positive, this is negative. The energy is negative. And let's look at the consequence of this. Suppose I want to plot, right? Take this and I plot V by L cubed. Or, I can plot, let's say, V over L cubed. Okay, as a function of temperature. As a function of temperature. Let's think about it. If the temperature is very high, right, if the temperature is very high, imagine, lots of molecules at the temperature is very high, it will be in a gaseous state. In a similar way, if the temperature is very high, right, the monomers will not be coming and getting attracted. Okay, they will be repelling all the time, right? They will go away, they will expand. The monomers will go away from each other if the temperature is very high. So when the temperature is very high, that means that Urij is going to be positive. That means repulsive. If they are repulsive, right? Let's go in here. Minus U is very highly positive, large number, positive. E to the minus a large number is going to be 0. It will go down to 0. Therefore, this first term in the square brackets is going to dominate over the second term in the square brackets. So this is plus 1. This dominates in this square brackets. This is an integral. Therefore, this V is going to be positive. So this is going to be here is a positive and negative. At a higher temperature, it's going to be positive. Right? That means what? That means if it's positive, that means it's a right. It's a repulsion. The segments are repel. If the segments are repel, then they are going to be spread out. That means solvent molecules are permeating in here. This monomer prefers to be away from this monomer. Therefore, this polymer chain is in a good solution of expanding. So we call this condition to be a good solution condition. Right? We'll call this to be a good solution condition. No, I should have done that. It is good solution. Okay. Now let me look at the other limit. Suppose the attractions are important. If the attractions are important, then I have U to be negative. If U is negative, please look at this. U is negative here. If this is negative, then I have a negative sign here. Negative times negative quantity is positive. So E to the positive number is larger than 1. Therefore, the second term is going to be dominant over the first term. So I have 1 minus this quantity. This is going to be bigger than 1 and negative sign. Therefore, the whole square bracket will become negative. If that becomes a negative and you do this integral, this V is going to be negative. So it's going to be somewhere here. Right? It's going to be negative here. Let me do this color. Negative. Right? So that means it has a cross between, when I lower the temperature, it has to go from here to there. It has to do something like that. So this condition, when V is negative, right, that means V is negative, that means this is attractive, right? URij is attractive. When it's attractive, that means this monomer prefers to be near this monomer because they are attracting. That's more prevalent in comparison with the high temperature situation. And therefore, if it's like this, then the solvent molecules are not going to be in the neighborhood. Solvent molecules will be outside. Therefore, the polymer doesn't dissolve in the solvent. Therefore, we call this condition to be a poor condition. We say this is a poor solvent or poor solution. But what is important here is there appears to be a temperature which is neither poor nor good. So I go to this temperature, that seems to be a special temperature. That special temperature, right, I'm going to call this to be theta. So at that temperature, right, the attractive interaction and repulsive interaction between segments appear to cancel each other out. Therefore, superficially, it looks like there is no V. V is equal to 0, right? This is 0 here. V is equal to 0 at that temperature. There's one unique temperature for a given polymer and solvent combination where the external volume parameter, which comes from this interaction energy, appears to be 0. And this temperature is called Flory temperature. Flory temperature, it's called ideal temperature. Ideal temperature or a theta temperature. Right? This is a special temperature. It's called Flory temperature, ideal temperature, theta temperature, or Flory theta temperature, things like that. Now you understand why we saw polystyrene in cyclohexane at 35 degrees Celsius is obeying Gaussian statistics because it is that temperature. For polystyrene cyclohexane, the theta temperature is 35 degrees Celsius. If you change this solvent to decalene, then theta temperature is not 35 degrees Celsius, and as we argued, it is different, right? That temperature is, as you know, it's 15.2 degrees Celsius. So when I change the chemistry, the theta temperature changes. There is, for every pair of the polymer and solvent, there is one unique special temperature, theta temperature, where there is only one temperature. If the temperature, take polystyrene, if the temperature is higher than 35 degrees Celsius, then I will have repulsive interactions between segments. If the temperature is below that theta temperature, then attractive interactions will become important, right? Therefore, you will not see Gaussian chain statistics. Okay. All right. So this is where we are going to account for the inter-segment interactions, right? Please notice there's a Kuhn segment length L that also depends on chemistry, because that tells you about the persistence length of your polymer chain. That is along the trajectory of the polymer chain, along the skeletal chain, and how they are put together in terms of trans and gauche. That depends on chemistry, but that is along the chain backbone. But the chi or V we talk about, and that is a measure of inter-segment interaction. That is, right? That is coming to the interaction between this and this, between this monomer and that monomer, between this monomer and that monomer, right? And between this monomer and the neighbors, that is created, that is captured by the Kuhn length. So there are two important variables in this problem, right? The way we are parameterizing chemistry. One is in terms of extrude volume parameter, other one is in terms of the persistence length. Okay. Now what I like to do is I like to go and discuss how do we account for this extrude volume interaction. Okay. But as you can see from this, you can imagine, or you can take for all practical purposes, you can take V as, right? V as roughly as a pairwise inter-segment interaction energy. Right? Throughout my lecture, whenever you see V, that's what this means. Average pairwise interaction energy between two segments in units of kT. Okay, that's the English sentence for this extrude volume parameter. Please do not think that it is a volume, and it's not. It is a volume that is excluded by one monomer for another monomer, and that is not the meaning of. Although in some books people talk about this to be an extrude volume, it is not the volume that is excluded, right? It is really a parameter which basically gives me an average interaction energy in units of kT. Okay, that's the parameter. Okay, so now what I'm going to do is I'm going to include the consequence of this, and I'd like to look at how does it affect the size of a coil. Okay, and this takes me to the Flory theory of chain swelling. Flory theory of chain swelling. Already when I say chain swelling, I'm a kind of implying chain swelling means the segments are going to ripple. This means I'm assuming that V is positive, right? Because go back here, right? It can, chain can swell only if V is positive. That means the temperature is larger than theta temperature. Only if the temperature is higher than theta, V is a positive, right? Therefore, this means T is larger than theta. In fact, near theta temperature, near theta, V goes like a T minus a theta by theta. Because, because experience tells us near the theta temperature is a linear. Look at this, V is a linear in a near theta temperature. Therefore, we can assume for all practical purposes, when you are very near theta temperature, V is a T minus theta, divided by theta to make it dimensionless, if you like. Okay. All right. Now let's look at the consequence of this. So my goal here is, right, I have a polymer chain. Right? And let's say it has a coil radius. So this is the coil. Let's say there is some radius here. Right? This is a typical coil radius. Typical coil radius. That's what I want to figure out. What is it? Because I know that this is not equal to, right? This is not equal to square root of n, because this is true only for Gaussian chains, right? Only at V is equal to 0, this is true. But here it's not going to be true, right? No, it's not going. In the presence of V, it's not going to be true. So what do I have to do? I have to do the following. The free energy of this chain. Let me try the free energy of the chain. It's going to have two parts. One is what we already did, free energy due to chain connectivity. Right? And then the other part, right? The chain is connected just like a Gaussian chain, right? That's the connectivity. Now on top of that, I need to worry about free energy due to excluded volume interaction. Energy due to excluded volume interaction. Okay. Now let's look at the free energy due to the connectivity. That we already know. This part we have that's a Gaussian chain. We know that, right? So this is equal to, right, 3, if you go back, right, F, let me call this to be entropy. The chain connectivity gives only entropy, remember? Free energy by entropy, kBT, is equal to 3 by 2 R square divided by NL square. We had this result before. Right? This is the Gaussian chain result. Okay, so now what I have is, for the extra volume interaction, let's calculate this. Okay, so I go to a small volume here. I ask myself, what is the probability that the two monomers will come close to each other? If they come close to each other, the interaction energy is V, because I told you V is average pairwise interaction energy. Okay, so what I will see is, V is pairwise interaction energy. Then I ask, what is the probability of finding two segments in one location? Probability of finding two segments at one location. That's easy, because the probability of finding one monomer in some location is a density, that is number of segments per volume. Volume of this coil is R cubed. The probability of finding two segments in the same location is density square, that is N divided by R cubed squared. Because N over R cubed is the probability of finding one segment, right? N is the number of segments, R cubed forget about 4 by 3 pi, right? No, forget about the numerical factors. So R cube is volume, right? Therefore, N over volume gives me average segment density. The probability I'm going to find is one monomer is average segment density, that's N over R cube. The probability I'm going to find two of them would be square of that, N over R cube square. But then it's not the only location here, right? I have the whole volume. So what is the free energy for the whole coil? Then I have to multiply this by R cubed. So this is, right? This one gives this second term. This one is volume of the coil volume. Okay, coil volume. So that's what we have. So the extra volume interaction energy, right, that will be V times density square, N over R cubed square times R cubed. Therefore, I can write the free energy to be total free energy. Oh, I made a mistake, right? So this one is only, so, okay. I should not have put plus sign there. That's like here. Okay, so like that. Okay, so this is the free energy due to the chain connectivity. And this one is coming from this red term. That's the free energy due to extra volume interaction. Therefore, the total free energy, I write free energy by KT, KBT is equal to, I write the free energy due to entropy by KT plus, I'm rewriting this expression, free energy due to, let me write excluded volume, extra volume interaction here by KT. Okay. Therefore, what I get is, I will get, this is equal to 3 divided by 2 R square over NL square. Then I have plus this quantity, right? I already told you in the previous page that V is in units of KT. So I have already accounted for this KT in here. Therefore, I get plus V N square divided by R cubed, right? Because I have N square there, R cubed square, that is R to the 6 in the denominator, and R cubed in the numerator. So I get V times N square by R cubed. This is a very beautiful result because what it tells me is if R is large, right, then, right, this term is weak because when the chain is expanding, R is very large, and then it's basically the free energy goes up because it is entropically dominated. Because when I stretch the chain, the number of conformations is reduced. Therefore, entropy is reduced. That means free energy goes up. But on the other hand, right, if extra volume interaction dominates, suppose R is small, this entropy is not important, R is small. Here, R is up in the denominator, the free energy goes up again. So free energy goes up. So if you want to plot a free energy, according to this, free energy versus R, if R is large, free energy is large. When R is small, free energy is large again. So there will be some optimum value here. There will be a free energy minimum at some value. Let's call that free energy minimum location to be RF. You know, this F is Flory. So let's call this to be Flory radius. Flory radius of the coil. So we are going to figure out what that Flory radius is. How do you figure that out? Right? This is the minimum. Therefore, I take the derivative of this free energy with respect to R and find where the minimum is. Let's do that. So by KT, I rewrite it again. 3r squared by 2nl squared plus vn squared by r cubed. Okay. So let's do df by dr. And that's equal to, right? Derivative of r squared is r, 2r. So I have 3r divided by nl squared. And then I do this red term, r cubed in the denominator. So what I will do is negative sign 3vn squared divided by r to the 4. Okay. And then I told you df by dr is equal to 0 when r is equal to rf, right? When r is equal to rf, that's the minimum. Therefore, I take this equation and equate to be 0. This means, okay, this gives me rf by nl squared, or f then n squared is equal to this term vn squared divided by rf to the 4. Therefore, I get a very important result. Therefore, I get rf is equal to v. Solve this. Rf factor of rf, bring rf to the 4 to the left-hand side, bring nl squared to the right side. So you get v, right, times the L squared, if you like, power 1/5, and then I have n to the 3/5, which I'm going to rewrite to be simply, forgetting about Kuhn length, everything, v to the 1/5 and n to the 3/5. This means, right, RF, the radius, is proportional to n to the 3/5. And I defined, in general, I defined, going back to previous things, I defined R to be n to the nu. Remember that? We defined that. This means nu, right, this exponent nu is equal to 3/5. Not half. This is called Flory exponent. So the Flory's argument says that in general, right, in general, independent of the chemical details, if V is important, V dominates, we will get this result. And this means also means, suppose I plot logarithm of R, right, versus a logarithm of N, right? Or I can even define, okay, or I could also define, okay, logarithm of R versus logarithm of N, right? Okay, instead of logarithm, okay, if I plot logarithm of R versus logarithm of N, then I'll get a straight line with a slope of 3/5. Okay, that's what this will turn out to be. Now, what I like to do, since we are kind of running out of time before we take the break, what I will do is I will replot this result in a different way. I will also show you external data to compare with. Then we go and look at the next hour. We're going to look at what happens in here. Okay, this is what is happening here, what happens in here. And that's what we are going to be doing in the next 45 minutes. Let's take a 5 minutes break.
Yeah.
Oh. June Fang, you tell me when I should start, okay?
Okay. Hello, Professor. We will start at 2 minutes later.
Okay, take your time, no hurry.
Okay.
Yeah. Are you folks? You ready?
Hey, could we start now?
Sure. Okay. All right, so we stopped here, right? We did this Flory calculation, right? We took the extra volume interaction, which was the red term, this term. We added this contribution to this contribution, and then we minimize the free energy. And when we minimize the free energy, we get this result, okay? So therefore, what we expect is if I plot, for example, radius of gyration as a function of temperature, suppose I take this and I plot as a function of temperature, here is my theta temperature, right? This is my theta temperature. At this theta temperature, I will have some value here, radius of gyration, At that special location, Rg will go like n to the square root. If I take this Rg and make a measurement of molecular weight as a function of molecular weight, then the difference of Rg on molecular weight will be square root of n at that special point. But when I go to high temperature, somewhere here, when you go to temperature here, high temperature there, right? Somewhere there, it would be n to the 3 over 5. Nu is equal to 3 over 5, right? And I did not say, right, how this crossover is going to be. Of course, the crossover is going to be something like this, right? And somewhere here, it will not be n power 3 over 5. This is n power 3 over 5 only in the high temperature limit. So how do we do this? How do we describe this? This is done based on what we already talked about before. Remember, the free energy for chain connectivity is not only this form. We had some corrections, right? Therefore, if I want to write the full expression, free energy over kT is equal to 3 by 2 R square over NL square, going back to our previous notes, minus 1 minus log R square by NL square. Remember that? Right? And then adding this X volume term, V N square by R cube. If you do this, this is the full expression. Remember? Because this is true not only for an extremely expanded case, right? But also in general, this is true. So if you take that correct expression for chain connectivity, and if you do this, you can show, in fact, when you do these calculations, it turns out there is also, remember, I'm forgetting about 4 by 3, etc., etc. I'm just missing all those things, right? So if I do all of those things, what happens is, right, this expression, instead of simply writing 4 by 3, if I account for all of those things, I get the following expression. Okay, that's equal to, let me write down properly. It's equal to 4 by 3, right? 3 over 2 pi power 3 halves. It's in the handout. The halves. V is the X volume parameter, and then I have n squared by R cubed. If I take all the factors into account, 3, 4, 5, all the numbers into account, this is the correct expression. Instead of being sloppy, we are trying to get the exponent, the Flory exponent, so we did not pay attention to the various prefactors here. But if you do that properly, that's what you get. Then again, it's very easy to do this calculation, right? You can do dF by dR is equal to 0. Oh, sorry. dF by dr is equal to 0. If you do this, you get the following expression. Alpha to the 5, where alpha is called chain expansion factor. Chain expansion factor. That means, right, that means R over divided by R square. It is the Gaussian chain, right? Square root. This is basically R divided by square root of n times L. This is my definition of chain expansion factor. This is equal to alpha to the 5 minus alpha cubed. That's the formula that comes out. If you minimize this, that's what you get. You get, again, 4/3, 3 over 2 pi power 3 by 2. Then you get V times square root of n divided by L cubed. That's what you get. Okay. Right. When alpha is very large, chain expansion is very large, right? As you can see, this means, right, alpha for V square root of n very large, for V times square root of n is very large, it is a large number, that means alpha to the 5 is going to be more important than alpha cubed. Okay, and this means alpha to the 5 goes like, putting all the numbers in here, V times square root of n. This means R goes like V to the 1/5, right? Alpha is R over square root of n. Therefore, alpha to the 5 will go like R to the 5, and then take the square root of n to the right-hand side times n to the 3/5. Of course, you must get that, right? Because that's a Flory exponent. So for asymptotic limit, R goes like V to the 1/5 times n to the 3/5. That's this number. That's that number, right? And then in the crossover, okay, when let's say when V is equal to 0, for V is equal to 0, right? In the special case, the extra volume parameter is 0. What would you get? Right-hand side is 0. Therefore, alpha to the 5 is equal to alpha cubed. That's possible only when alpha is equal to 1. When alpha is equal to 1, we go back here, alpha is equal to 1, R is simply square root of n. That is the Gaussian chain result. For this particular case, R goes like a square root of n. Therefore, what I'm trying to say is this formula that I have given here, this box of formula gives me that crossover, right? This box of formula gives me how it moves from Gaussian chain limit at theta temperature, that's that number, to the asymptotic Flory exponent results n to the 3/5, right? Here, and the way this moves around depends upon this quantity V times square root of n. That's an important thing, right? Depending upon the value of that, you have a crossover. Suppose if the value is such that you are not sufficiently large, then you will not get this 0.6 power law. Particularly for people who do simulations, I want them to appreciate that you will not get 0.6 all the time. All depends upon this important quantity V times square root of n. Only if V times square root of n is sufficiently large, you get that exponent. Otherwise, you get something in between, an exponent of half and exponent of 0.6. You may get 0.54, you can make it 0.56, something like that, 0.55, depending upon the nature of V times square root of n. Okay. So we can also, let me look at RG as an example. If I take RG, same thing, right? So let me define alpha, instead of this alpha, let me define for radius gyration, alpha s square, let me define. That's equal to RG squared divided by RG Gaussian chain result. Let me define that. Same thing, alpha, instead of alpha, I'm defining alpha squared. Okay. And then in this limit, right, in this limit, R is proportional to RG. Okay, R is proportional to RG. So what would you get? Alpha S squared would be proportional to, right? RG is proportional to R, RG square is proportional to R squared. So I will get a V to the 2/5, right? And then R is proportional to, right? R is proportional to n to the 3/5. Therefore, R square is proportional to n to the 6/5. Then multiply by and divided by RG square. RG square is proportional to n. Therefore, I'll get n to the, if I do this, it'll go like n to the 6/5 divided by n, capital N. Therefore, it'll go like n to the 1/5. Okay. Therefore, if I plot linear plots, suppose I take alpha s squared and I plot this as a function of n to the 1/5. Suppose I do this, I should get a straight line. Because I'm plotting, right? In this, I expect alpha S square, which I can measure. Remember, I know how to measure radius of gyration experimentally. Remember, we did this in the beginning of today's lecture. And we know how to measure molar mass. Therefore, I can construct this experimentally. This green quantity I can measure. I take this measurement and I know n based upon the intercept. I plot alpha S square versus n power 1/5. If Flory theory is right, I should get a straight line. Okay, now let's check this. Now let's check whether this is right or wrong. How do we do this? Let me go to, let me show you some experimental data. Oh, yeah. Look at this. Isn't it beautiful? Alpha S square as a function of n to the 1/5. This is one polymer, this is another polymer, this is another polymer here, another polymer here. Independent of the particular polymer-solvent combination, right? And I'm telling you also, I want to show you a little bit. So here, when I say PHB, it is that polymer in that solvent. And when I talk about PS, polystyrene benzene, not cyclohexane 25 degrees, right? And on and on and on. These are all different polymers, different solvents. And what you get is a straight line, alpha S square versus square molecular weight power 1/5. It's a beautiful straight line going through the origin. Okay, that means Flory's exponent is correct. It is a validation of Flory's exponent. Now, I know in a in-person class, I'll be calling some people and asking, well, what does that slope correspond to? Why are the slopes different? They're all linear going through the origin. That means alpha S square is proportional to molecular weight power 1/5. Why is the slope different? The answer is simple. Slope is different because that slope is the extra volume parameter power 2/5, right? Extra volume parameter power 2/5. That's what we will show. And I showed you in the previous slide, right? There's 2/5. And then the extra volume parameter depends on chemistry, depends upon the pair of the polymer, chemical nature of the polymer and chemical nature of the solvent, right? So that is a validation of going back to our last thing. Yeah, so here alpha S square is proportional to the 1/5, and then that slope is V to the 2/5. Okay, so that's end of the discussion for extra volume interaction when we have repulsion. That is this branch. We are talking about this branch. This branch we have now completely understood because T is higher than theta. When T is equal to theta, V is equal to 0. We know V is equal to 0, we have Gaussian chain results. When T is larger than theta, V is positive. Depending upon the magnitude of V times square root of n, we'll have the crossover behavior from theta behavior to complete good solution behavior. Asymptotically, we'll get a Flory's exponent 3/5 for molecular weight, size exponent. Now, next what I want to do is, I like to go down and look at what happens in this situation when T is less than theta. Let's go to the expression that we had here. Let's look at this. Now, suppose, right, we do this, right? You have entropy, and we have the extra volume interaction, but now V is attractive, right? When V is attractive, what happens? When V is attractive, this becomes a negative. Then I have a positive quantity, this is a negative quantity. Then I'm looking for free energy minimum. And when I have this negative quantity, when I decrease R, when the R is becoming smaller and smaller, and then this becomes a larger, 1 over R. R is small, it becomes larger, but it's a negative sign. That means this curve will go down to be, free energy will become negative. Eventually, free energy minimum would be when R is 0. It's like a black hole. That is the whole polymer chain becomes a small point. That is not possible. That's not physical. Because I told you when monomers get close, there will be immense repulsion because the nuclei cannot overlap on top of each other, right? Therefore, what we need to do is we need to worry about additional interactions. When I bring monomers together, closer and closer, it's not only pairwise interaction I have to worry about, I also have to worry about three-body interactions. Okay, so now let me go to the next question of how I'm going to deal with attractive interaction between segments. Okay, the next one, I'm going to take a topic. I'll call this to be coil-globule transition. Coil-globule transition. That means, right, I have a coil like this, right? And there is an interaction which is attractive. If it's attractive, the chain will come, the monomers will come even closer, more and more like this. Then there will be an attraction between this and this and that too. So I have to worry about three-body interactions. Three monomers can come close, and they will be repulsive because they cannot sit on top of each other. But I have to worry about that. Therefore, the free energy, in this particular case, free energy in units of kT is equal to the entropy contribution, R squared by 2 NL squared. Sorry, let me not worry about 2 here. R squared by NL squared. So 3 by 2, I don't want to talk about it. Okay, forget about it for the time being, because we want to be simple-minded. Forget about numerical factors. We are interested in the exponent. Okay, so that is coming from entropy. That is, we ignore prefactors, numerical prefactors. Then I have the two-body interaction term, right? The two-body interaction term I would write to be V n squared by R cubed. But I know that V is now negative. So in here, I'm interested in V is a negative. That means T is less than theta temperature. And as I'm telling you now, V now would be equal to, very close to theta temperature, theta minus the T by theta. Okay, let me define like this. V, right, theta minus T, like this. So that means, right, when V is negative, I'm going to put explicitly the negative sign in here. Negative, I put like this. Okay. Previously, I had a plus V n squared by R cubed. Since V is negative, I want to explicitly write down the negative sign, but therefore the modulus of V is a positive quantity because now temperature is below theta temperature, right? So T is less than theta temperature. Now I want to look at the three-body interaction terms. Now, how do I do that? The three-body interaction term, I would say, okay, let's repeat the same calculation that we did before. V3 is interaction energy for 3 segments when they are coming close. Then I will write n over R cubed, that's the density, power 3. This is probability to find 3 segments in one location. Right? Some location there. Then I have to worry about the free energy, the whole polymer chain. Therefore, I put R cubed. So this is a volume. Okay. So therefore, what I have now is, right, I have an expression like this. F over KT is equal to R squared by NL squared, right? And then I have negative V modulus n squared by r cubed. Then I have this term plus V3 n cubed by r to the 6. Okay. And what I want to do is I want to minimize this. But now you can see when r becomes small, right, this becomes large. Three-body interaction becomes large, right? Then there is going to be a compensation between this and this, right? And also please notice when r is small, since since the chain is collapsing, when r is small, this is going to be dominant over this term. This is going to be dominant over that term, right? On a pocket calculator, you can minimize this, but intuitively we think since r is going to be small, these two terms are going to dominate. Okay? They are going to dominate over the entropic term. In any case, we are going to make minimization of the free energy, dF by dr is equal to 0, and that is going to give me the following results. From the red term, right, leaving out all the numerical prefactors, right, there's a minus 3, 1 over r to the 4. And negative sign will cancel out. Therefore, the red term will give me V modulus n squared by r to the 4. Okay. And then the green term is going to give me a negative number, minus 6 over r to the 7. And then since this is going to be 0, I'm going to take that to the right-hand side. So this is equal to, I'll write V3 n cubed over r to the 7. Therefore, I get a very nice result. Therefore, what I get is bring r to the 7 to the left-hand side. Therefore, r to the 7 divided by r to the 4 will give me r cubed. Bring this modulus of V to the right-hand side, right? Denominator of the right-hand side. N square will cancel out the n square factor. So what I get is r. I'll get a beautiful result. R going like V3 divided by modulus of V over 1/3 and n to the 1/3. That's what you get. Right? There's a factor of n squared, there's a factor of n squared here, therefore I get n. And r cubed will go like n, therefore r goes like n to the 1/3. And then V3 by modulus of V power 1/3. Okay? It depends upon the distance for temperature from the theta temperature, depends on that, and depends on, of course, molecular weight. But this is very beautiful, intuitively obvious, because remember it's more like a globule. The exponent nu, right, for nu exponent is 1/3. This is like more like a compact sphere. That means the fractal dimension is now like a real Euclidean dimension 3. R cubed is proportional molar mass. That's what we get. Okay, as a consequence of this, what I will do in view of this, what I will do is I go back to this picture here. Now I'm going down in temperature. Temperature is below theta temperature. I'm going down in here. What I get is now I get a globular state. So let me redraw this picture once more for completion. I get, say, I plot RG versus temperature. And here is my theta temperature. Somewhere here is my theta temperature. And there, oh, let me draw, this will move better. The temperature is somewhere there. And then I showed you in a good solvent, I get that result. Here, nu is equal to 3/5. And at this point, I have theta temperature, that's equal to nu is equal to half. And I told you that this one is in a good solution condition. Good solution condition. Then I'm lowering the temperature. I go down here, and it turns out to be like this. Here, nu is equal to 1/3, and I call this to be a globule. Globule, this also means poor solution, as we discussed already. This is the poor solution. Okay, and this is a coil. We call this to be a coil. So that's why we call this a coil to globule transition. So these are the three important exponents: 3/5, half, and 1/3. Okay. Now what I like to do is I like to show some experimental data, whether it makes sense. Okay. Does this make sense? Let's do that. Before that, to help you out a little bit, to interpret the experimental data, let me rewrite this expression. Okay. How do I do this? I have an expression R, and I like to write in terms of this expansion factor alpha. Expansion factor alpha is equal to R by square root of N. Okay. And since R, this is equal to, since R is this quantity, this goes like 1 over V modulus square root of N. Maybe I can put V3 if you want, V3 by square root of N, power 1/3. Okay, because R goes like V3 by modulus of V power 1/3, N to the 1/3, N to 1/3, N to the 1/3 divided by square root of N gives me 1 over N to the 1/6, which I'm writing like this. And I already told you, therefore, I can write alpha cubed times V times square root of N is simply a constant, some number, which is V3. I take the cube of this, alpha cubed times the modulus V times square root of N is a constant. What is V? V, I already told you, is something like this, theta minus T over theta. Okay, so that means if I plot alpha cubed versus this V, which is theta minus T by theta times square root of N, suppose I plot like this, as a function of theta minus T by theta times square root of N. Suppose I plot like this, it should be a constant. When alpha is very large, it should be a constant like this. But when alpha is 1, that is V is small, right? If a V is really small, theta is very small, for smaller values here, it should be a straight line. Because then alpha is equal to 1, imagine alpha cubed is 1, then I'm plotting Y versus Y, right? I'm plotting Y versus Y, therefore it will be a straight line. And therefore what I would expect is, I would expect the globular region, I would expect a behavior like this. If I plot alpha cubed times theta minus T over theta times square root of N versus this variable, it should look like this, which is this result, which is the result that we just derived. So what I'm going to do is, I'm going to show you external data. Make sure our thinking is correct. Okay. So here is an example of polystyrene cyclohexane. Okay. Please remember, we showed the theta temperature to be 35 degrees Celsius. Remember? That's what we showed. So this is my theta temperature. For temperature higher than the theta temperature, the chain expands. At the theta temperature, the radius gyration is 207 nanometers. The radius becomes bigger and bigger and bigger. And then here, the Flory exponent of 3 over 5 is valid. And the reference is given in the handout. This is in the reference, okay? I have given, that's, when you go and look at my lecture notes, you have this reference. Okay, so we got that. But when you lower the temperature below theta temperature, the chain shrinks. So you analyze these data. And these are not very simple experiments because of fundamental polymer physics. These experiments were carried out by Professor Benjamin Chu using beautiful light scattering measurements, extremely careful light scattering measurements. And those data are summarized in here. So I'm plotting the same way, right? I'm plotting the same way I indicated before, alpha cubed. This tau is theta minus T by theta, square root of molecular weight, versus again, theta minus T over theta, square root of molecular weight, and that's a straight line plot, and eventually it becomes flat. This is the globular region. Here, the exponent is 1/3. The exponent is 1/3. And please look at the molecular weights. We are talking 40 million molecular weight, 8 million molecular weight. This is a beautiful work, extremely hard work. But this is how we make progress in making understanding. So with all this hard work, we are able to validate the arguments that we are able to make to make an understanding, right? The argument is what? The argument is basically this. There's a half a page derivation with a paper and pencil calculation, right? But that gives a tremendous strength to appreciate the volumes of experimental data. Okay, so this is the spirit with which we are composing these lectures. And we want to put down the foundation, conceptual foundation to understand the variety of phenomena associated with polymer physical chemistry, polymer physics, polymer science, polymer technology, and polymer engineering, right? So please appreciate how simple a calculation of this type is and how that is able to provide so much insight in interpreting the data. So that keeps me on time to complete this picture. So going back to this picture then, what I have is this one. I have a coil, extrude volume interaction dominating, repulsive extrude volume interaction dominating here. And then for temperatures below theta temperature, I have a formation of globule with the size exponent 1/3. And that's a crossover, which I showed you experimentally. And also theoretically, you can do very similar calculation that you did before. That is, we got this calculation. So you repeat the same kind of calculation again, you will be able to capture this green curve, complete green curve. Okay, so now I like to take a pause for 30 seconds. And I want you to think about this one, just to summarize this. And I'm going to add a new twist to this argument. I'm going to take a small pause. Think about it. Make sure you are comfortable with this. Then I like to go back to an argument that I made in the very first lecture. Okay, so let me go, while you are looking at this, let me go to the very first lecture. There. You remember I told you about the persistence length, chain stiffness. And I told you that given a chemistry of the backbone of the polymer chain, if you lower the temperature, right? If you lower the temperature, independent of what the energy difference is between the gauche state and transit state, if I sufficiently lower the temperature, the chain will become stiffer. This is particularly true for semi-flexible chains, right? We talked about, right? So when I lower the temperature, I would expect the chain to become stiffer. I also told you about semi-flexible chains. I think I told you in the last lecture. Remember this? In the Kratky-Perot chain, and then the chemistry of the backbone is such that, right, it can become rod-like. I told you that, right? It can become rod-like. Persistence length is large, that can become rod-like. So either the temperature is low enough or chemistry of the backbone of the polymer chain is such that it is semi-flexible. If that's the case, then what will happen is, going back to our figure here, what will happen is there will be another branch. If the polymer is a semi-flexible polymer, then what will happen is, I'm looking for a different color here. What will happen is, maybe I'll use this color. What will happen is, there will be a rod-like at low temperature is low, I'll have a rod-like conformation. This is nu is equal to 1. That means a rod-like. When I increase the temperature, then persistence length will come smaller and smaller. It will become flexible chain, but eventually, since we have extrude volume interaction, it will meet with this line here. So this would be called a coil-rod transition. So this will be rod, right? Rod, and here is coil, and this is globule. So we'll have coil to globule transition, coil to rod transition, depending upon nature of the chemistry. And depending upon where you are in terms of temperature, I will have an exponent 3/5. You will have an exponent 1/3. I can have an exponent 1. And depending upon the crossover, I may be able to get an exponent which is neither 3/5, nor 1/3, nor 1. It could be some effective number. In general, I can write down R can be n to the new effective. New effective could be anywhere in this map. It could be 0.78. It could be here 0.4. It could be here 0.56, right? It could be anywhere, any number. But the theoretically, asymptotically valid theoretical values are, these are 3 boundaries. For the coil, swollen coil, 3/5. For the theta condition, which is special condition, means equal to half. And for low temperatures, globular state is 1/3. For rod-like situations, 1. And this could be any number. But from now on, I'm going to write R is equal into the new. As far as single chain is concerned, dilute solution, this is the final sentence. In general, whether the polymer chain is a branched polymer, a flexible chain, semi-flexible chain, whether it's a good solvent, poor solvent, marginal solvent, somewhere in between, we will have this, and there will be an appropriate value nu. Okay. This is the foundation of all our next lectures. Now, from next lecture onwards, I'm going to go to higher concentration. I'm not going to talk about dilute solutions. I'm going to go and put more and more polymer chains into my vessel, in my solution, in my beaker, and I want to understand how they are going to interact. But this is going to be the foundational sentence, because this sentence is valid for all these situations. All the chemical details, quality of the solvent, all those things, the temperature, they all appear through this sentence. Okay. And this is a very good stopping point, right? This is the summary stopping point for today. And if you don't have questions, I can spend the next 3 minutes to say something that was asked in the last lecture by D, if that's necessary.
Hi, Professor.
Yes.
No more questions.
I can't hear you, Junfan. I can't hear you.
We now have no questions.
Okay, all right, fine. So let me add only one more sentence, and then we can stop, right? I'll add one more sentence and we can stop. This is in response to the question that was asked in the last lecture by Dija, right? Suppose I have in general, I have an object like that, right? Like that. Then what I do is, let me go and look at, it is a 3-dimensional system, right? Let me look at a volume, 3D. Okay, let me say D is equal to 3. Let me look at some volume, at radius R. This is the center of mass, some radius R. So I look at some volume element there, at some volume R, right? Some radius R. Then the density, right? A density at R is equal to mass, right? Number of segments in that volume divided by volume, R cubed in this case. That's the density. Density is mR by R cubed. M is the number of monomers in that volume, some volume. Suppose you make a R radius R, I define some radius there. right? In that spherical volume, 3-dimensional, mr by r cube. But if it is self-similar means the structure is the same. Whether I look at this region or that region, looks the same to me. If it's a self-similar, right? mr is proportional to the r to the nu. I'm sorry, r to the 1 over nu. Remember, the last sentence is r goes like n to the nu. Therefore, n goes like r to the 1 over nu. So that m in that volume element will go like r to the 1 over nu. So this means rho of r goes like 1 divided by r 3 minus 1 over nu. So in the self-avoiding case, self-avoiding means that this good solution case depends on nu. In the good solution case, for example, this goes like 1 over r to the nu is equal to 3/5, 5/3, right? 3 minus 5/3 will go like r to the 4/3. So it's a power law. The density rho of r falls like 1 over r to the 4/3 for a good solution. But nu is equal to 3/5. But in scattering, what you do is you measure density in a momentum space, the scattering vector k. This is integral of d cubed r rho of r e to the exponential e to the ik dot r. This is the Fourier transform, e to the ik dot r. Rho of r is this. Therefore, I do this integral d cubed r, right? This goes like dr r square in 3 dimensions, 1 over r to the 3 minus 1 over nu exponential of I to the ik dot r. You can do the scaling argument. You can put, since k dot r comes in here, I can write this, but you can do the integral. If you do this, this becomes 1 over k to the 1 over nu. This is why we said this goes like 1 over k to the fractal dimension df. Okay? If you do this integral, this simply turns out to be rho k is to be 1 over k to the 1 over nu. That's why 1 over nu is a df. So the connection between the fractal dimension and the monomer density distribution, which they are connected by Fourier transform, it's actually this proof. Okay? This is true for any self-similar objects, because please notice that the 3-dimension does not appear here. Here, there's a 3-dimensional integral. Here, 3-dimension in here, they cancel out. This is also true in any dimension. So this is a very general proof of self-similarity. Okay. So this is a side remark. Going back to the argument that I made before, today, right from the beginning, going back to here, remember, I showed you for large K or J, namely, I'm interrogating the internal structure, self-similarity, the scattering intensity, which is the form factor, goes like 1 over k to the 1 over nu. So what I'm showing here is a general proof of how that comes about. So this is a remark, a response to the last question. Okay, but I think this is a matter of detail. But the important thing for you to know is this picture. This is the most important picture that you should know. You should remember. So this finishes, a foundation for a single chain. How we are going to deal with single chain. This is done. And next lecture onwards, next week onwards, we'll talk about many chains. Okay. Jun Fong, I think I'm done with what I wanted to share. Again, I give you a minute. See whether any of you have questions, either you or the students.